are the gas busters. These days, e-cars are not used due to their many problems. There are not enough charging stations, they have slow charging time, the batteries don't last long, it's expensive, and they're not green at all. Most e-cars get their electricity directly from fossil fuel burning plants. So we're going to implement the infrastructure of a system of e-cars to the German town Hamburg. Hamburg aims to ban all cars from the city center by 2034. We aim to provide an even better solution. E-cars.
On average, Germany has about 588 cars per 1,000 people. If Hamburg has a population of 1,800,000, then there would be 1,058,400 cars present. We aim to change 50% of these cars to e-cars. Therefore, there should be 529,200 e-cars in Hamburg. Our targets are to use eco-friendly resources, have a longer lasting battery, improve charging infrastructure, and the efficiency of charging. First, let us start small, the e-car itself. The average capacity of a battery of the car is 30 kWh. If the user chooses to, due to its high cost, we could use solar as the secondary source. One of the main problems with batteries in e-cars is that it runs out quick, so the solar panels will make it last longer by charging it while it is being in use, or while it is parking. Usually, such an idea would not work, but we are using a Fresnel lens canopy designed by Ford early last year. It is positioned above the car to boost solar exposure several times over. It can harvest 50% more energy over the surface area than conventional cells. It is a type of compact lens originally developed in lighthouses acting as a magnifying glass. When parked underneath the Fresnel canopy, the car will track the sun and roll slowly backwards or forwards to keep the most intense area of the solar energy. So, as an alternative energy source for batteries in e-cars, flywheel energy storage devices work by accelerating a rotor to a very high speed and maintaining the energy in the system as rotational energy. They can maintain 97% of mechanical efficiency. As a comparison to batteries, flywheels are less dependent on temperature and are not subject to chemical failures. They are also more eco-friendly and potentially have indefinite working lifespan. The amount of energy a flywheel stores comes down to its mass and the speed at which it rotates. Prototypes have provided a 60 kilowatt-hour boost. We plan to use two types of charging stations. The battery swap station. It tackles the limited range of electric cars and the cost of the battery. Customers will have to buy their first initial battery and swap it at the station every time their car needs to be immediately charged, while still paying the fee of the electricity at 0.35 US cents per kilowatt hour. As renewable energy varies over time, the batteries at the stations can be charged at times when the energy level produced is being high. There are also wireless charging stations installed in parking areas in towns, high streets, and houses accessed by subscriptions. The power of the wireless charger is 7.2 kilowatts. If the battery needs 30 kilowatt hours, it's going to take about 4 hours to be fully charged. These charging stations will be located in distances at every 10 kilometers. On average, in Germany, each car travels 33 kilometers a day. That's 6.6 kilowatt hours a day for each car. Thus, the entire town would need a total of 3,500,000 kilowatt hours a day. These are our energy sources. For solar, we are going to use 80,000 square meters of a multi-crystal solar panel on the roof or on the walls of the surrounding houses and buildings. This would allow us to generate around 8.5 times 10 to the power of 5 joules per day. And for wind, we need about 11,000 wind power generators, and this would require around 6.875 square kilometers. Now this will generate around 9.5 times 10 to the power of 12 joules of energy. Now with solar and wind combined, we would get 1 times 10 to the power of 13 joules of energy. The stations in the city need an average of 3,500,000 kilowatt hours a day, which is around 1 times 10 to the power of 13 joules of energy. To supply this power, we use a smart grid. This links generation, transmission, substations and storage, distributions, and consumers. The demand and supply must always be balanced.